So, do a quick review of what we've done in the past so far. So the last thing we dealt with was the scenario where you have two data sets, two groups really of data, and we had the model where we both groups, we said, okay, they've got a normal distribution. So let's call this mu1. We didn't know where the center of this group was. Mu2. We didn't know where the center of that group was. But we decided that, and both groups have a variability, but we decided they had the same variability. Oops, sigma squared. So this sort of emulates the t-test, where you've got two groups. You're going to assume they have the same variability, but you don't know what that variability is. There's chairs back here, Chris. So for each of these, so this is our generative model for the data. We assume that the data were generated from normal distributions. This group from one with mu1 and sigma, this one from mu2 and sigma. In the actual stand code to express that generative model, I'll actually, where did my session go? Okay, I'll go to downloads. I think 5 is the one that had this set up, and I'll open up the stand and I'll pull it out as its own file window. Okay, so, oh no, 5 is not the one that had the what we're talking about. 4.
4 was the last thing I'd opened.
Yeah. Okay.
Because it was still there when I opened.
So open up 4 and open up the stand file. So again, what I've drawn here as our generative model. Here, two normal distributions. They both have the same sigma, a different mu, a different sort of center parameter. That's expressed in the stand code by the last two lines here. We've got data for one group. It's being normally distributed with some center mu1 and some other thing called sigma. Data from the other group, normally distributed, centered on something called mu2, but using that same sigma. Now, this generative model has 3 sort of unknowns, mu1, mu2, and sigma. So that's what we put in our parameters section here. mu1, mu2, and sigma being a variability parameter can only go as low as 0. It can't take negative numbers. So we have to, that's why we have this lower equals 0 there. Now, with each of these 3 unknowns, these 3 parameters in our generative model, we can express our priors for those parameters. So here, this actually is going to look a little different from what you have because I've done something a little different. So let's see. I think what you guys had was sort of a prior of 100. Sorry?
120.
120.
120.
120.
And then 2.7,
2.7, and 2.3. Okay. So what this set of priors expresses is that we think that the mean for one group is somewhere around 100, plus or minus 20. The mean for the other group is somewhere around 100, plus or minus 20. And this weird line is talking about what our prior for sigma is. And this one is, since sigma is lower bounded at 0, it probably doesn't make sense to use a distribution that can go into the negative. You could, and Stan would handle that okay, but I prefer to use the log normal for variability parameters. That lets you set like where its peak is. So unfortunately, the numbers that you put in here aren't like the numbers on the data scale. They're on the log scale. So another way of doing it, actually, to make it so that it's easier to look at, is to do that. If you say log of, what did we say, 7? So this is the way to specify a log normal distribution that's peaked at around 15 on the data scale and has sort of a variability that's, when we drew it out the other day, it seemed reasonable. I actually drew it wrong, so this is a really large variability. It doesn't hurt because, again, bigger variability in our priors. Whoa. Did I run out of power? Oh no, it just scooched down. Gotcha. Bigger variability in our prior simply reflects sort of less certainty. So more variable priors are okay. It just, yeah, go ahead.
When you write your paper, do you say what priors you use?
Yeah, typically you do. Ideally, you put all your code online so everybody else can replicate your entire analyses, try their priors if you chose particularly strongly informed priors.
So when you're like picking your prior and then like putting it in your paper, like how do you justify the prior that you picked?
Well, that's what I thought I'd show you next,
Okay.
is a way to be sort of relatively uninformed about this. Question.
I think I asked this last time. I'm still confused about it. What's the difference between like the mu parameters and then the sigma parameters?
So the sigma, so whenever you've got this normal something comma something, the first something is where the center of the normal is going to be. The second something is the standard deviation of the
Right.
normal.
But like the 100 versus and 20 versus
Gotcha.
the 15.
Okay, so same idea. We're using the normal. Here we're using the normal to say how data were generated. And up here we're using the normal to express just a general shape. So the normal is useful as sort of something to talk about a shape because we can talk about where it's peaked, which is that thing here. But also how it sort of generally falls off on either side of the shape. So this is still a standard deviation, but we're using it more for the general shape that, like, if you have a distribution centered on 100 and a standard deviation of 20, most of the sort of mass of the distribution falls plus or minus 20, just like most of the mass of a general normal falls plus or minus 1 standard deviation. So that's all it's being used for. If we wanted to be less certain about where mu is, then we just increase this number. Say we said it's around 100 plus or minus 100.
Okay.
That sort of
so
reflects.
why don't we use those same parameters for the sigma?
Well, because this is talking about how certain we are about where this value is, or this whole thing talks about our credibility in different values for where this mean is. So if I were really certain that mean was right around 100, 100, 101, 99, I'd express my belief saying normal 101. Alternatively, if I wanted to be really uncertain, I'd say plus or minus 100. But that's, again, referring to where this parameter is, where the group's mean is. This one down here talks about, okay, whatever the group mean is, how much noise is there in each group? Like, if I were to sample one person, it'll have one value. If I were to sample another person from the group, they'll have a different value. And how much sort of difference from one person to another will I expect in the group?
And then we put the log 15 and log 7.
So in order to talk about like what we should believe in terms of how much variability there is from one person to another, we previously had examples where we didn't have sigma as a parameter. We had, let's see, this gone, and we had 15 and 15. This was a scenario where we were assuming we were dealing with IQ scores, and we assumed that we were certain that the variability we'd find in the population from one person to another was precisely 15. But maybe the population is slightly different from that expectation. So if we wanted to be uncertain as to how much noise there is in the population, how much variability from one person to another there is, we would make this a parameter, in which case we'd want it to both give it a heads up that this is a parameter, it's lower bounded at 0, and we'd want to express what sort of our beliefs about this is, that the potential values that this could take would be. So we might have a peak belief at 15. That's the way the IQ test was designed. But we might believe 14 a little bit. We might believe 16 a little bit. And that's what this expresses as sort of a smooth distribution reflecting the credibility of different potential values for how noisy the population is one person to another.
Is it possible that you would have different priors for the different groups?
Yes. So this expresses sort of the common t-test scenario where you're assuming each group comes from some unknown but common variability, but is entirely possible. In fact, it's shown in the file or the folder 07, I think, that you could actually have a sigma 1 and a sigma 2, in which case you'd need this to be sigma 1 and sigma 2, and you'd need prior on both sigma 1 and sigma 2. So that is an entirely possible scenario. Indeed, that is sort of the more flexible scenario. So whereas you need to jump through some hoops to get around the assumption of homogeneity of variance or equal variance assumption in frequentist world, you can just implement two different sigmas in the Bayesian world.
And that's all you need to do. That's
Yeah.
fine, even if they're like completely different.
Yeah, all your inference comes out perfectly valid.
Okay, so I just want to make sure I understand. So with like the original example you have with only the one sigma, so we have two groups. We're pretty sure that both groups, the mean's going to be around 100 for what you have right now. We're like not really sure it's going to be around 100 for group 1. We're pretty sure it's going to be around 100 for group 2.
Yeah.
It's
probably a rare scenario. You
and-
probably have the same
And that
confidence in both.
we don't know what the standard deviation is for both groups, but we're pretty sure that they have the same standard deviation.
Yes, in fact,
Okay.
yeah. The way it's structured right now,
Okay.
this
And we-
assumes they have the same standard
Okay.
deviation.
And we think the standard deviation is around 15, but we're like only kind of sure about
Yeah.
that. Okay.
Yeah, exactly.
Okay.
Yeah.
Okay, cool.
Mm-hmm. So, this is a scenario where you have pretty good prior information on what sort of is going on. So, scores for IQs are generally around each group should probably be near 100, and the variability should probably be about 15. What do you do if you are completely new to a domain and you don't know what those scores are? Well, there's a trick to make it so that you can have sort of a standard set of priors. So I'm going to go into the code associated with this data, this folder, 04, and I'm going to pull that out too, just so I can flip between this more easily. Okay. So, remember the way this code works in each of these folders, it actually is generating data as if it were sort of your God at the outset, and you're creating data. So this is creating fake data. Yes, okay. So this is creating 30 observations from one group whose true population mean is 97. And true population sort of variability, standard deviation is 15. So that's going to be in Y1. But this is a sample, so even though the true population mean is 97, there's our observations. If we look at the mean of this group, it may be a little different from 97. Indeed, it's at 100.4. And if we looked at the standard deviation of this sample, it's not precisely 15, it's 13.7. So again, this is the population values.
Did you set the?
I did not.
Okay.
So good call. That's why you're getting different numbers. So I'll set the seed, and then I'll run this again. And the mean is one value, and SD.
Randomized seed.
You can choose a random seed, like you can, but that wouldn't make sense
No.
because then it's back to being completely random. Like you can't then replicate that seed. Okay, so we asked for 30 samples from a population whose true mean is 97. We got 30 samples. The mean here that we got of their sample is 98. And the standard deviation of our sample is 13.8-ish. So, again, samples will deviate a little bit from their population values. Ditto will do the same thing for another group whose true mean is 108.
One small question. What if we had a population of 30, say, 3 million? Would it be very
Probably
similar to the population? Our
Yep.
sample would
Yep.
be more similar?
Yeah, or if you had, instead of 30, if it was like 3 million, the central limit there, or what is it, a law of large numbers,
Yeah.
would sort of suggest that the value that we got for the sample would be very close to what the population mean was.
Or if we knew the actual standard deviation to be much smaller, then we would be closer. Even if it's
Imagine running just a 30. And a
Yes.
3 million.
Um, Okay, so that's one group. We'll generate the other group. The other group has a true sort of population mean of 108. So its sample mean is 109.9. So if we were to have these two sets of data, not know how they were created, and we're curious, sort of, are the populations that created these two sets of data equal or not? Well, if we had all that knowledge that we had before, that these are IQs and that they probably are distributed with sigma of 15-ish, and they're probably centered around 100, then we could use those to set our priors. But what if, like, this is a new domain for us? Say these are blood pressures or something like that. I don't have that much familiarity with blood pressures, so I might not be comfortable setting sort of where the priors are for those two things. So a trick to doing it is to rescale the data as z-scores. Does anybody remember how z-scores work? You take the mean of all the data, and you take each observation and you subtract that mean. So it's like you take, if you imagine a histogram of the data, you've shifted it over so that the mean is now 0. And ditto, you want to rescale it so that most of the values fall between -1 and 1. So you divide by the observed standard deviation. Let's actually do that.
So this is if we don't really know what to set our priors on?
Yes, this is sort of working up to a scenario where we're going to use what's called some default priors. So the trick is to compute z-score, to transform your data to some standard scale. And the standard scale we'll use is the z-scores. So to compute the z-scores on y1, so we'll create something called y1z. And I'll say, so we need to take each y1 and subtract from it the mean of y1. And the result of that, we also need to divide by the standard deviation of y1. Everybody follow? First, you subtract the mean from each y1. that yields, again, a bunch of numbers, each of which you divide by the standard deviation of y1.
Is there no like standard notation just to do it without having to do the math?
There's a function that does it, but it'll be more complicated to describe the function than it would just to show that. So, and let's just double check. Afterwards, we should have a mean of what?
0.
0. And we should have an SD of what? What was that? Mumble? 1. Okay. So mean of, well, not 0, but this number is sort of as close to 0 as the computer can store. So without, yeah. When you do math and then you try, when you have like the expected scenario of something eventually equaling 0, sometimes the number looks weird, but that's pretty much as close to 0 as we can get, and the standard deviation is 1. Awesome. So having scaled y1, we can do the same thing for y2. And print out the mean and the standard deviation. So now y2 has a mean of 0 and a standard deviation of 1.
You mean a mean of 3. Oh, right.
Pretty much
The
0.
negative, right. Yep,
Yeah.
gotcha.
So what's wrong about this? I mean, we've got the result that we wanted for each group, but what's going to happen when we subsequently try to compare these two z-scores? Yeah, we've centered them both on the mean of 0, so of course we're going to have a result of, if we say mean of y1 minus mean of y2, that is a number that's non-zero. But if we look at the mean of those z-scores, the differences on the z-scores that we just computed, it's basically 0. So, I mean, that something we've done doesn't make sense. So the thing is that we've standardized them within each other, within themselves. So we actually want to refer to like the mean of both y1 and y2 and the standard deviation of both y1 and y2. A quick way to do that is to create a thing called both that contains both y1 and y2. C means combined together in sort of a single list. So if I type out both, there's all 60 numbers. And now instead of the mean of y1, I'm saying the mean of both, the standard deviation of both.
Could you also just have done the both at the end and said both y1z, y2z?
No, because the both, so we need to get the mean of both groups and the variability of both groups together there. So what this should yield is z-scores where, like, the mean of each group actually will be slightly different from 0. And ditto, the standard deviation of each group is going to be slightly different from 1. So what does this mean? If I say, in fact, compute this thing we had up here, mean y1z minus mean y2z, it says they're different by 0.8 somethings. What is 0.8?
Standard deviations.
Yeah. So the means of the two groups differ by 0.8 standard deviations. Standard deviations of what? Well, deviations of like the two groups that were combined together in the first place.
Sorry, can you go back down?
Yeah.
Yeah.
How does that math?
Take the two means, subtract them from each other.
So we've created this thing called both, which is all the means together.
Oh, sorry. I was looking at the mean of the standard deviation. I was like, how is 0.4 minus 0.8 minus 0.8?
Right. Can you keep walking through those somewhere? Am I
Yeah.
wrong?
Okay, so we created this thing called both, which is just the combination of these two things. And
Print out for both, but then it goes wrong.
okay, and then we create this thing y1z, which is y1 minus the mean of both, divided by the SD of both.
Wait, why is it y1 minus the mean of both and not both minus the mean of
Ah, because we want to talk about, we want to just rescale y1 first.
both? Oh, okay.
You could have done it that way, but then you would have had to figure out which numbers afterwards were associated with which group.
The Cohen's d is that divided by.
Right, yeah, now it's fine. That's what my problem was.
Mm-hmm. So, again, this number here, the difference between the two groups is 0.8 somethings. That something is the variability we observe sort of across both groups in all their raw numbers.
The variability you experience between both groups across all their numbers.
Yeah, so all the IQs that you measured, regardless of groups.
Across all raw data.
Yeah. Yep. Now, having set the data such that like a given like magnitude of a difference, I guess each number represents a z-score, and that again kind of represents units of the variability. You can kind of think of this now as each of these numbers reflects. Let me actually just type out y1 z, there y 2z. Okay, so there's all our numbers now, having been z transformed. So this number means it's 1.1 standard deviations away from the overall group, like the mean of all the group, where the standard deviation is how variable the groups are, all the scores are in the first place. So we still have a difference between these two sets of numbers and where their means are. And that difference is on the scale of how variable scores were from one to another. So you can think of this as like a signal to noise ratio, in that if you talk about the signal as being the magnitude of the difference and noise being how much variability you just observe in the data on its own without classifying it in one group or another. One would reflect a standard deviation of 1, or a value of 1 means that there's precisely as much difference between the two groups as there is variability or noise in the data overall. So that makes it
Sorry, can you say that again?
Sure, yeah. Again, the thing we're scaling by is the amount of variability we observe just looking at the data without having these labels of which group. So how much person-to-person variability in IQ is there, or blood pressure. So another term for that, like person-to-person variability, is noise. How much noise is there? So if we actually measure that noise and rescale every data point as a proportion of that noise, then any value we talk about down here is talking about, or any sort of difference we compute is on the scale of like signal to noise ratio. So a value of 0.8 reflects there's a difference between the groups that's 80% the magnitude of the amount of noise that we'd observe across the groups.
Okay, so sorry, that last part again. So,
Mhm.
so the point it would be like there's an 80%.
80%, so the difference we observe between the two groups
Yeah.
is 80% the magnitude of the amount of noise we observe in the data set.
Which means what?
Well, if you start to get like experience with just any data set or any domain of data, you generally start to see that most phenomena that we study tend to have signal noise ratios that are probably less than 1. Like the world is pretty noisy. So a difference that's like 10 times greater than noise would be very unlikely. A difference that's like half the noise, so 0.5, would be a little bit more likely,
Okay.
more credible.
So in this case, it's really unlikely.
So, well, what this is simply saying is that the observed difference
Yeah.
is about 0.8 the size of the amount of noise that's in the data, the typical amount of noise that you find in the data. So it's the exact same thing as effect size. You guys are used to effect sizes. It's a magnitude of a difference over some measure of variability,
Okay.
if you remember that formula. And that's exactly what we're doing. We're talking about the scale of effect sizes. Let's say put it in those terms. So psychology, most effect sizes are like 0.2, 0.3 if you're lucky. Like unheard of is like 0.8. So by rescaling the data in terms of these z-scores, you're effectively making it so that you can start specifying your priors using your understanding and your good information about effect sizes, not about the specific domain we're talking about right away.
Okay.
So
So the
Yeah.
main difference there is like the effect size in this
Yeah,
case.
yeah.
Okay. And then we're gonna use that like as a prior knowledge of effect size since we didn't really have prior knowledge.
yeah, we didn't have prior knowledge of this specific data, so we can use our prior knowledge of effect sizes that we might encounter in our career or our field. So we've already sort of, let's say, let's talk about the variability parameters, I guess, or sorry, the certainty. Shoot. This is a lot easier to talk about in the next example, but lest we...
If it's
Yeah.
easier to talk
Yeah,
about the
just
next
do
one,
it.
it might be useful to because I don't want to change this file, which has.
Mm-hmm.
You know what I mean?
Oh, okay.
I mean, we can. I'll just
well,
make a new
in theory, we've scaled so that the each population, we've got the mean of both groups is now closer to 0 than we had before. Technically, if we actually look at the data, there we go. The mean of y1 is negative something, and the mean of y2 is positive that same value. So by doing this mean of both groups, subtracting from each group the mean of both groups together, we've made it so that both groups are kind of centered near 0. Does that make sense? To the degree that the groups actually differ from one another, their individual means will shift a little bit away from 0. But just knowing that we scaled the data in this way, subtracting the common mean from each one, means that we can assert a prior that's centered on 0, and that's probably a pretty decent prior for that, for both groups. Similarly, I mean, we expect the groups might differ a little bit, and that's going to influence how that scaling affected things. But not much more than a whole effect size of 1. So the consequence of scaling using that method means that we can assert prior of 0, 1 on both groups, and it'll work fairly well. in the sense of it's a pretty broad prior still. There's still a chance for the groups to differ by more than 1. But we expect both groups to be around 0, and they might differ from one another by a little bit.
Given that most psychology studies are like, you see 0.2 or something,
Yeah.
right? Could you put that in as your, instead of 1, put in like 0.2?
Yeah, you could be more certain that they are much closer together.
Right.
Um,
So based on previous research, you can.
you can, if you had that sort of expectation. The larger prior, 1 won't be very troublesome. If you put it at like 1,000, that will start to be troublesome.
Right.
But yeah, I would suggest sort of having done that standardization, 1 is sort of reasonable. There's enough mass above 1 that you're going to catch higher effect size phenomena, but it also is reasonably.
Sorry, is this one your like effect size, or is it still the like distribution of your prior?
That's the distribution of our prior, but it's on the scale of effect sizes. So again, the thing in this position is specifying the standard deviation. You're saying that plus or minus this contains most of the mass. So I'm saying plus or minus 1 effect size unit will capture most of. I will believe studies within plus or minus 1 Cohen's d unit or whatever.
So, but I'm just like where putting that at 0.2 would be really small.
Yeah. So
And
it would say I'm very certain that both of these means are really close to 0. So
An effect size of 0.2 would be.
It's not an actual effect size. Like it's the equivalent of an effect size.
But that's
not.
But that doesn't make sense because it would have the opposite. Like
I'm thinking of like you standardized your data
Yep.
to be centered with a mean of 0 and a standard deviation of 1.
yeah, that's what I understand.
So how can you be that certain that the true mean is? I'm confused.
I'm confused because to me, an effect size of 1, like it's equivalent to the effect size, then it should be the opposite,
But this isn't the standard deviation of the data.
Correct.
right?
This is the certainty of your guess, right?
mhm.
Of,
Yes.
of mu.
So
So you would your 1
But a
that you're
smaller
talking
effect
about,
size would mean you have less.
the 1 would go into the sigma.
you're
Right.
okay. I understand. Yes. So think about this value in this world where we're going to be scaling our data as reflecting sort of the plus or minus on the effect size scale that you wouldn't be very surprised that your actual observed effect size would fall into. So if you were pretty sure that the effect size is between 0.2 and negative 0.2, you'd put a 0.2 there. If you were pretty sure that but if you were less sure about that it would be somewhere close to 0, so you thought that 0.5, 0.6, those would be reasonable values, you'd maybe bump that up to 1. And I actually would do that. I'd leave it at 1 myself because there are some big effects. Yeah.
How certain we are about where the effect
Yeah,
size
it's
is,
like
not
plus or
the
minus.
effect size itself.
Yeah.
Okay, that's
Yeah.
what was confusing. Is that what you mean?
Yeah.
Mhm.
Yeah.
Mhm.
Sounds like,
And
yeah.
this example is somewhat confusing because we're still talking about each individual mean all on its own, and effect sizes are about the difference between means. So it's a little hard to think about. The next sort of twist we'll do is changing how this is structured so that we can talk about that thing that we are most interested in, which is the difference between. Before we get there, let's finish off here. This log normal, again, is talking about how variable the populations are within themselves. Now, we standardize the data, so it makes sense for, well, if you look at the values for each one, the standard deviation of 2 was 0.8, standard deviation of 1 was 0.9. so we've actually scaled it by the variability of both. So 1 is like sort of a good sort of belief here that you expect each group to have like a sigma of 1. But maybe it's a little less than 1. Maybe it's a little greater than 1. That's how we've kind of defined the data in the first place, that 1 is the amount of variability you find like within a group. So to get it so that we have got a log normal distribution with a peak at 1, well, we could say log of 1, put that there. Anybody happen to know what the log of 1 is? Yeah, it's 0. So you could just put it at 0. And ditto, just for symmetry's sake, in this domain, a useful thing in variability is just to put a 1 there. It actually means that, like, on the raw scale, the normal has like a variance of like 2.3-ish, but it looks pretty when you have 0, 1, 0, 1, 0, 1.
So if we were to write it how we had before, where we actually did like the log 15, log 7,
Yeah.
it would be log 1 and then log.
Yeah, whatever, I guess, the XP of 1 is, or log of whatever that is. But, yes, just 1 there is fine. Here, if you wanted the other way, log of 1
Then I'll understand.
and log
Yeah, because
of...
you're plugging in your standard deviation.
Yeah.
It makes sense.
Because otherwise I'll look at that and be like, well,
Because
why
log
is it
1
all
is
0 and 1?
If you did log of like 2.3 or log of 2,
Okay.
that creates a nice...
And we're picking the 2 based on what again?
So
Our
where it's
certainty about-
peaked
Yeah.
is at 1, because that's kind of how we defined the data by scaling it. So we expect 1 to be a very likely candidate for the amount of variability, and then this just establishes wiggle room on either side.
Okay. And
So how much wiggle room? I actually think that you could even put that as log of like, what is the, yeah.
You wouldn't
But-
put
You'd want 1 to be the answer, right? Maybe?
But so the lower
2.7.
that number is, the more certain you are
Yeah, that
your
it's-
sigma is the log of 1.
but so you wouldn't where you have the log 1 for the mean, you wouldn't put the mean of the y1 z and the y2 z? You wouldn't put that there instead? That was the mean of
No,
your
because this is
standard?
the amount of variability that you're observing within each
Right.
group.
Okay.
So, like, the analogous value you can compute from each group is the standard deviation within that group. So this one, the standard deviation of 2 is about 0.8. Standard deviation of 1 is about 1.
So we're kind of rounding up.
So, yeah.
So why wouldn't we use those actual values then?
Because usually the priors are kind of supposed to be without seeing your data yet.
Okay.
Now,
Okay.
and 1. I mean, we expect both those values to come out to near to 1, given the way we scaled.
So in a way, this prior is kind of like a null hypothesis. It's like they're both mean 0.
Yes. So that's one sort of important thing, is that by centering each mean on 0, and we had this before when we centered each mean on 100, that there's an implicit null hypothesis. The prior was like implicitly having greatest credibility of a difference of 0.
Say that again.
So having each, so the way this is parameterized, we've got a mean for each group, but they both are centered on the same numbers. So the difference between these two numbers is 0. So we have peak belief in a difference between these two groups of 0.
That's where it's like most credible.
Yeah. It would be a lot nicer. So we can run this model, but it would be a lot nicer to be able to actually directly talk about the thing we're most interested in scientifically is what the difference between the two groups is. So that's where folder number 5 is going to come. I'm going to copy this a little bit because... Oh, where'd it go? Well, I guess I hid my files section over here. Folder number 5. I'm going to open up this. But, oh, actually, even before I open that up, I'm going to do some drawing. Okay, so we still have this same scenario where we've got two groups. They're going to have a common. We're going to have a model that has them as a common mean, but we're going to shake up how we're actually reflecting sort of the numbers. Let's imagine a scenario where instead of a bunch of numbers from each of two groups, we've just got 2 values on a number line. So this is just something categorical. So this is A and B. But this is our actual measurement. Here's a measurement for the thing labeled A, and here's a measurement for the thing labeled B. So there's 2 ways to think about this. One way to describe these numbers is how far is this one from where y is 0, and how far is this one from where y is 0. So in fact, that's actually what these numbers on the side represent. So let's say this is 5 and this is 15. Another way of describing those same numbers is a little weird. It's to say, where is their center? So it's 10. So you say, where is the center relative to 0? And then, how far is it from the center to either one? So if these are the actual numbers, 5 and 15, the distance to the center is 10, and the distance from the center to either one is 5. 5 or negative 5. Does that make sense that you can describe these two numbers two-way, either with how to get to them from 0, or how to get to their center, and then from the center which way to get to each value, how much sort of you have to move from the center to get to each value? So the distance from 0, that's kind of like the mu1 and mu2 method. We're going to use a different, that's the mu1, mu2 parameterization. We'll use a different parameterization where we call this distance from 0 to their center the intercept. And the distance from the center to each one is, we'll call the effect. Or actually, I think in the code I call it difference.
Is this similar to intercept and slope in growth model?
Yeah. Like you can actually, that's, if you imagine the slope is the distance between.
But isn't the intercept usually where?
It hits 0, yes. Except if you happen to arbitrarily call this one -1 and this one 1 and call the 0 there, intercept becomes the center point between those two.
Oh, so it's as if your y-axis is actually like where that center
Yeah.
point is.
Yeah.
Okay, cool.
Yeah. So this is the intercept and slope parameterization, intercept and effect. I think in the code I call it, instead of mu1, mu2, I have a single mu that really is the intercept, and I call the distance between them diff. So let's actually look at that code. Yeah. So
I don't have that RDA file.
no, you don't. This gets created when you compile the model with certain things. Okay, how come this isn't opening? Oh, because it already is open, and there it is. So there we go. pull it out into its own. So, with this parameterization, you have the data coming in the same way. You've got one vector that's y1, one vector that's y2.
Oh, sorry, so we're in the 5. Okay.
Yeah, 0, 5. So the data is going to come in the same way. The way the model is structured, though, is different, so the parameters are different. Instead of a mu1 and mu2 in sigma, now we've got mu. You could just call that intercept, and diff, which you could equivalently call a slope. But we still have sigma, because the model still has sigma there. Nothing has changed about sigma. Still lower bound at 0. We still have the log normal prior on it. And it's still being used as the common sort of variability parameter for the generative model that is saying y is normal with some mean plus sigma variability, and y2 is normal with some mean and sigma variability. So what is the mean that we're saying? Well, we're saying that it's mu plus or minus some difference. There's plus for y1 and minus for y2. So just like we had in the graphic here, to get to each point, you have to go up at least some amount, and then up or down some other amount.
But if you don't know which one is higher or lower than the intercept, how do you know?
That's going to change the sign of the difference.
No, I know, but so how do you know, like,
Which one is?
Yeah. Because we're supposed to do it like thinking we haven't seen the data, right?
Yes. Yeah. So you just assert a sign ahead of time.
Okay.
So I put plus difference for y1.
Oh, so that just makes y1 the one that's above it and y2 the one that's below it.
Well, what's actually going to happen, if it turns out that y1 is below center, this diff parameter will be driven to negative values. Because plus a negative value means go down, and minus a negative value means go up.
Oh, okay. Gotcha.
Yeah.
Okay.
So it doesn't actually matter which one gets the plus and which one gets the minus in the actual sort of math here, because this can take on positive or negative values, and the sign of that will reflect which one actually has the larger mean and which has the smaller mean.
Okay. So as long as we just have one of them assigned as plus and one of them as minus.
Yeah. Yeah. So notice I've said diff divided by 2. That's merely for convenience of afterwards, like doing interpretation. If I want to talk about the total distance between the two, then I would have a parameter for that total difference. But to get from the center to either one is half the distance. So that's why you say get from the center to this one is half the difference. Get to the center to this other one is half the distance.
Is this just a different way of doing what we were doing in the other?
Exactly. Yeah. But the nice benefit of this one is that instead of having mu1 and mu2 and an implicit, so in the same priors for mu1 and mu2 and therefore an implicit prior for what the difference between the two groups might be, we now can have an explicit prior on the difference between the two distributions. So here we're saying that a Cohen's d of 0 is the most credible thing. A Cohen's d of 1 is decently credible, but sort of Cohen's d's of plus or minus 1 are more credible. We don't really believe Cohen's d's greater than 1 so much.
So this is it's like actually.
This literally
actually
is
effect
Cohen's
size.
d.
Yeah,
This
okay.
is your
Makes
prior
a lot
on
more
effect
sense to me,
size. Yeah, exactly.
Can you explain that again? Like the mu versus the difference?
Yeah. So let's actually so mu again is where the data is located, Now we've scaled the data so that the common mean should be about 0. So makes sense to put 0 there. And we want to be uncertain about like where the population's mean is. So putting a 1 there is actually overly uncertain, but it's fine for this scenario, for most scenarios.
So can you just go back to the picture for a minute?
Oh yeah, sure.
So in theory now.
Yeah, in theory, by scaling, we
zero on
have
the dotted line.
yeah,
10. Okay.
0 is on the dotted line, or it's where 10 is.
Yeah.
We don't really know what this distance is because
Yeah.
the size of that distance is the amount of noise sort of we observe within each of the groups, but it's probably about, well, we don't know how much noise there is within each.
What we're saying is
Yeah.
it's within 1.
Yeah,
So between -1 and 1.
yeah. The noise is such that most of the data fall between -1 and 1.
And so the 2 points on the two sides are like the two groups you're comparing, and then
Yeah.
in the middle is the population.
Yeah, so this is sort of the mean of the two groups without paying attention to what group each person is from, whereas this establishes the amount of difference that there is between the two groups.
And how do we decide that again?
Well, so if you actually had prior information that these two groups are different, so let's say lead exposed kids to non-lead exposed kids on IQ, you might have sort of a nice prior that, oh, okay, I expect sort of a difference of about, I don't know, 0.4. You might have, for a scenario like that, you probably have precise numbers for the difference. But maybe you expect an effect size of about 0.4 for that difference.
Mm-hmm.
Even if you went into an experiment with that sort of prior knowledge, a general practice is to sort of account for the fact that you might get reviewers that disagree with your analysis, and therefore it's better to center your prior for effects at 0, so that it's sort of, that's a way of phrasing that is as a skeptical prior. You will reflect most belief, least surprise in an effect of 0, but increasing amount of surprise away from 0. So even if your own personal experience is that, okay, I'm just replicating something that's been done many times, I'd actually be surprised if it were 0 and not be surprised if it was non-0. A skeptical prior nonetheless asserts sort of 0 as the peak of our credibility.
And this makes your analysis more conservative.
Yes.
This might be a weird question though, because the possible values are only 0 to 1, right? Like in terms of.
Cohen's d actually can take 0 to infinity.
So how do we why did we say 1, not 2, or 3, or 4?
Because I have some experience with things in my field generally, that most of our effect sizes tend to be sort of in the 0.2 to 0.3 range.
Mm-hmm. So could we do 0.5 as the top value?
Yeah, here it's sort of a range where it sort of has credibility over values sort of -1 to 1, but they start tapering off pretty strongly thereafter. If I wanted to be more skeptical and think that I actually think that most of the effect size in my field is around 0.2, and I actually wouldn't believe effect sizes much bigger than that, you would do that by asserting a more certain prior close to 0.
In this model for the sigma, are the values in the log normal coming from the same sort of idea as the last?
Yeah,
one?
so it's the same as log 1. It's actually slightly narrower than what I had before. Log 1 and log 2.3-ish. That's the same as 0, 1.
I have a question in terms of the diff and then the normal and the two numbers. I thought the 0 was referring to where the mean of the distribution of the prior would be, and then the 1 would be the standard deviation of that prior for
Yeah.
the next one down.
Yep.
But so if you said you had given the example of putting 0.2, if you thought that's what your effect size would be, but what isn't that number there referring to the standard deviation of the distribution?
Well, let's actually visualize these curves. Where's my R code? Oh, I closed it. So I'll just do it straight in R. So pull down my visual. So to visualize the normal curve, you can use the curve function. I think I showed you guys that the other day. And you give it the result of d norm. So in the same way that we've got normal 0, 1, we can have d norm 0, 1. We have to put x there because curve uses the first argument. It will set the value of x to a whole bunch of different numbers and evaluate this function. And let's look at the curve for the normal distribution from values, I don't know, I guess, from equals -3 to equals 3. And look what that looks like. So this is a curve reflecting this prior that we're asserting. This is just a visual of that curve. So peaked at 0. It's got a standard deviation of 1. So most of the more credible hypotheses fall between -1 and 1. You still have some belief in like hypotheses of about 2, an effect size of about 2. Not so much around 3. So what I was meaning by what happens if we are pretty confident that the field of effect sizes that we could expect to encounter are somewhere around 0. And we have the idea of changing that to 0.2. That would narrow up the distribution so that now 1 becomes like a relatively surprising effect size to observe.
If 0.2 was your most credible effect size, wouldn't that be where the curve should be centered?
Yeah, if you thought that most studies in your field came out with effect sizes of 2 and didn't account for the whole publication bias issue and things, then yeah, you'd want to shift this distribution over to 2.2-ish.
Okay.
So yes, that would reflect that. So shifting it over to about 0.2, but that ignores the fact that we know that there are unpublished studies with lower effect sizes that didn't get significant results. So probably better to center things on 0. And it's also reasonable to be less sort of skeptical, or not skeptical, less confident in the true effect size being so small. So that's why I like the 0, 1 curve. It still lets you, it still sort of expresses a reasonable amount of belief that the effect size could be big.
So if you actually do have a really big effect, because you're
Yeah.
an awesome scientist.
Yeah, I mean, to put it in the frequentist world, a more sort of uncertain prior, wider prior, will allow you to have greater power. A really narrow prior around 0 will provide less power to detect large true effect sizes because the distribution now has to shift quite a bit relative to its sort of narrowness. So generally sort of a nice wide prior will be good. Not so wide that, for example, if you had it at like 1,000, like that, or 100, I guess. Because if you look at what that means for effect sizes, Like, you pretty much have very little discrimination in terms of how surprised you'd be to find no effect versus an effect size of 10. So you don't want to get carried away with setting your certainty super high. But when you standardize the data using z-scores, a prior of 0 and 1 is fairly reasonable, fairly common to see. All right, so let's actually run this through. So I'm going to pull this over, open up the data generating part because I'm not sure. Oh, right, because we have, so this code, oh, no, it is number 5. Okay.
Does it have to expect y1z now?
Yes, it does. Let me. Let's actually skip to. No, let's not skip. Okay. This is slightly different code that is actually wrong. So I have to go back and get the code that we wrote a second ago from the 4 where we scaled it. So in 04, I'm gonna copy this bit where we create both. And I'll paste it into my example here. Okay. So I'm gonna generate the data, y1 and y2, create this thing called both, use that thing called both to rescale the data, y1z and y2z. When I package up the data, I want to actually give it y1z and y2z.
You just go.
Sorry.
Yeah.
Like,
Sorry.
Which parts we copy? Like,
I just copied the creation of both,
so
and then y1z, y2z.
like the clear list, set C1, and then didn't even use that big data. Like you didn't. Did you?
Yeah, I guess you guys, if you'd run it from the last example, I used the exact same seed and
But,
numbers.
If I
So.
cleared when I came over.
Oh,
would I do
okay.
that
So
again?
yeah, you'll want to select set seed, generate y1 and y2, and then do the standardization, the z scoring as you had before. Now when we package the data, we need to remember it previously, just the code had y1 equals y1. Now we want y1 equals y1z, y2 equals y2z. So that creates that little package for Stan.
Do you not have to do that for length?
Uh,
I guess it'd be the same.
It would be a good idea. They're going to be the same length no matter, because the scaling we didn't change the length, but good idea. So I think instead of taking the time to compile this model, I'm going to click this, and I'm pretty sure that will just create the model. Oh. All right, I need to set as working directory. Oh, and I need to go up one. So I set my working directory to the 05 folder, and I'll compile this model. It compiled really quickly for me because I previously already compiled it. So for you guys, it might take a little while.
If you get it. Okay. Mine keeps like that curved dealing thing that we did. Every time
Yeah.
I try to it keeps printing that, even though I'm not selecting it and I'm like clearing my workspace. It just keeps coming up.
Oh, you know what? This is actually an annoyance for me in RStan. If I say 1 plus 1, and then I don't do anything, and then I go type some other stuff, it stays there,
okay.
ready to be computed. So you just need to erase it from the console.
Thank you.
It's probably got something to do with
Wow.
invalid.
You
No, we're not there yet.
now something went awry with your install. Have you
Yeah.
did it compile everything fine before?
Yes, yeah, last week it was all fine.
Here, maybe you need
I
to
don't
run
get a
that.
warning message
I'm pretty
after
sure
you
I
finish
did.
compiling.
But let's try.
Sorry?
I got a warning message
No,
about
something.
highlighting.
Okay.
It said warning message in read lines, file, comma warn equals true, incomplete file line found on
Okay.
blah blah blah.
It's just complaining because it wants an extra line on this, and sometimes that gets deleted by mistake.
Why
I
does it
always
want
get a bunch of text.
Not sure.
I always get like this long line of text out, and it's got a couple warnings in it, but it doesn't seem to be doing anything, so I've just been ignoring it.
Yep. You can generally ignore those warnings.
Do I need to, if I add an extra line, do I then need to compile it again?
Don't even bother compiling again. Yeah.
Okay,
If
cool.
you get that extra line warning, ignore it. Yeah. So having compiled the model, I'm going to go to my evaluate the model section, but I'm going to delete all these extra things. So I just have the rstand sampling, object equals model, data equals data, C equals seed.
That's odd.
Wait, why do we have a line above out that says sampling iteration?
Because I had
Should we delete
some,
it?
yeah.
Okay.
All it was sort of by, so there's a default number of iterations that is just fine for this stuff. So I keep meaning to update the repos so that you guys can download it again and not have all this extra stuff that I keep telling you to delete.
Okay.
That's still on my agenda.
Okay, so default number of iterations is fine.
Yeah. And we can confirm that by running the sampling,
Like, no, but that shouldn't.
getting a printout of the result.
I got way different.
So our stand
why
loads,
did I
but
get an error?
I got
I think
another
so.
new error.
Could not find function CPP underscore
Like your
object
sigma is
or
100.
initialize.
Yeah. What's
Failed
I
to
got a
sample
mu of
or sampling
0.62, a
method.
difference of 0.01, and a
That's
sigma
what
of
I got,
100.
same as you.
I don't have the same as either of you.
I got an error.
Okay,
got
so people with errors. This just happened to you. Did you update your OS to Sierra? No?
No.
You guys didn't run any updates?
No.
For people that didn't get, okay, did you guys save when we changed the numbers in the two-group thing?
Mm-hmm.
Saved what?
Like where we made it 0, 1, 0, 1, 0, 1?
Yeah.
Okay, so did I.
So you've got your working directory set to 05.
Yeah.
Yeah.
You've got the stand file
Oh,
for
wait. No.
05.
No, it says it's set to 04.
Mm-hmm.
That's my problem.
Okay. You've got the stand file set to 05. So yeah, for the people with errors, I feel like
Yes.
something went awry with the install. So we're going to have to reinstall Stan.
How do we do that again?
Let's not do it. So I think for the purposes,
Oh, it's working.
like,
Wait, you got your story time?
I restarted everything and I forgot this time. I forgot to set the working directory when I changed. But now it seems to be
it's still
going.
the same directory, though. Yeah, that's weird.
No, I just said it. Oh,
But sorry, no, it's weird that it worked just by restarting your session.
yeah. Well, I closed our studio completely.
Yeah.
Yeah.
So he just made a new session and it works again.
Yeah, that worked for me last time when I was getting errors.
Okay.
Odd.
So I don't know.
I still don't know how I got completely different numbers.
I wonder if did you remember to when you packaged the data? Did you remember to package it with Y1Z,
Yes.
Y2Z?
Did you take out those variables that you took out for evaluating the model?
Yep.
I can have like
What
so many
But then you
things.
guys get the same number,
But I
which
can't
makes
wait.
sense.
But you
didn't
your
Here's
Like how different are you saying?
like really like a mu of 0.62, a difference of 0.01,
No,
which doesn't
that
make
should
sense.
be Y1.
Yeah, a sigma of 100.
And this?
And did you change your
You
scan
know,
code to match what you did?
random
Because the
figure
scan code that we
generator.
opened.
As a
Has a difference.
Yeah,
Yeah.
what's
Yeah.
your
Yeah.
second?
Yes. Oh, yes, all of the above.
Okay, so two group
It was Lauren's first baby.
Y1Z both.
I don't think she didn't
both.
notice it though. I said that to Sean. He died. It was-
1, 2, 5, 2, 4, 5.
It reminds me of this.
So yeah, you've got very
I meant to read that.
wide priors there. Or sorry, wide posterior.
Kara doesn't know. She wanted to go with
Oh
us.
my God, so Alright, well, I'll go to mine. You know mine. I haven't seen yours yet, but.
Double check my
Are
data.
you gonna go to your office?
Oops.
Alright, well, I'll come find you.
171, 116. Okay, so I believe you that you have the right data.
Oh, we'll here for a second.
Two computers.
God damn it, it just replaced that. But Perry literally got the exact same answers as me, which is weird.
I don't know why it's saying you can't find it.
0.01, 0 log 2.3.
Well, no, I was asking you to save that one.
I know, but I just.
Um,
And Y1 is up here.
Oh. Did that change it? No.
No.
okay, and you ran
No.
you made the both,
Mm-hmm.
and then you did these two things.
Oh,
Yes. Restarting it worked.
nice.
Right?
So that
Okay,
works.
So with that.
That works.
Mm-hmm.
That works. That works.
That's
Try packaging it.
sigma
Because you did get your
100.
bottom of your mouth.
That's particularly
Okay.
weird.
Mhm.
Sigma is 100.
Oh, it's acid.
That's fun.
Yeah, I like it.
All the data's the same though? Like seed and all that?
Oh, I don't have these in. I just have one.
Oh, you don't have practice.
Log
Yeah.
normal 0, 2.3.
Is this the output from just printing it?
And now it says campaign.
Oh.
No, this is. I was
Oh.
looking at the data. Let me.
Okay. I just
These
want to
should
make
be
sure I
just
got the same
Y1.
numbers from printing
I
it.
see
now
yours is
you
Y1.
Oh.
Does that
Oh
make a
my
difference?
gosh.
Unless you had.
Okay, I just found.
Unless you had.
Yep.
Why does it make? Oh,
Because
of the
it's
model,
looking
right.
for. Yeah, it's looking.
Okay.
That's what goes
So
into.
here, I'll show you the output
Oh, God.
from the
I
model.
Okay.
But that's something that actually
Because that's what's in here.
really
Yeah,
annoys.
that's what's in
Oops.
And you say.
It's weird that it still ran. Like,
Yes.
that there was no error.
Yes.
It is weird that it's
This
still
is
ran.
why I'm just immediately upset.
Oh, mine's not quite the same.
So what
I
was that?
have
That was not.
5.79 to 0.78 and the rest of the same.
So where we
Mine's
packaged the data,
479.93.
I had
Yeah.
Y1 underscore Z equals Y1 underscore Z,
25.46.
but not.
Of 26.14. But they're very close now. Before they were like, so.
You
Yeah.
run those lines.
I'm just running the model now.
What do we have to do, Sarah?
You gotta run that one. So
This.
Oh,
Yeah.
so you got
Oh,
the
you
exact
did?
same
Yeah.
result. Okay, so
Mine
what
is
happened with both you guys? Let me show you. I'd suggest you create Y1 and Y2, standardize to create Y1Z, Y2Z, and then remember to supply Y1Z as the value of the named thing
I
Y1.
had changed both sides.
She had put both sides as with a Z.
Oh, okay.
What I did is that I had Y1 and then bracket Y1 underscore Z. I don't know why, but.
My code was the same as yours, but I have slightly different output things.
So I.
Okay, yeah, it's because our CPUs are slightly different. Even when it's got the same
Oh.
seed, it can't guarantee the same numbers.
And
Okay.
they're
Yeah.
much closer.
So as long as they're like fairly similar.
Yeah,
it's-
exactly. Yeah.
Okay.
And I mean, if we were to increase the number of chains and increase the number of iterations, there'd be a point at which like we wouldn't be able to see the difference between our two machines.
Okay.
I just want to expound on this error not error,
there
but
that
this
didn't
weirdness.
came
It's funny that
I've been
that-
telling you to package up the data for Stan and give it the data through saying, here's the data. I am rather annoyed that Stan has the behavior of not needing to do that.
Time out.
This whole time we could have just had, as long as we had something called NY sort of in our environment, something called NY2 in our environment, and we already had Y1 and Y2 already there. It will look at its data definition and look for these things just in the general environment. It first looks at the list of things that you gave it, but it will also, if it doesn't find what had happened, we created this thing, data equals list, and a couple of you had it as Y1Z and Y2Z. So it looked in this list for something called Y1. It didn't find it. It should have failed then, but it didn't. It found Y1 out here that you created in your general workspace. I'm make a little note to complain to the Stan folks, because that is not behavior that is just safe.
Unacceptable
Because
behavior.
you only knew you only knew that something awry happened because I was here and you had different results from me. If you were home on your own
Yeah.
doing your own science, who knows?
Stan used them 100. Wow.
So to be safe, we should like provide
Yes,
it for Stan.
provided it explicitly
it doesn't
and
And make sure they're the same.
um.
That you have it in the Stan file and what you're providing.
Okay, so ask Stan devs about enforcing non-global lookup. Because there's no safe way to do it. Like,
Yeah.
So, I will complain and hopefully make them change it so that it only looks at what you give it. That way, it'll be much easier to catch those errors and not gracefully enter the scenario where it's doing something you don't want it to do. Okay, but assuming we got that going eventually, working great, let's look at the result. So this is much more typical to what you guys would actually be wanting to do in terms of inference, so that you had a single parameter that talks about the thing that you are interested in, the difference between two conditions. Here, if I were to encounter this, I'd say, okay, well, usually you could look at this stuff over here. Usually I look over it here. I'd say, okay, this distribution, for the difference, it's generally the 95% credible interval excludes 0, and it's negative. So it's been shifted negative relative to the prior distribution. Again, we had that prior distribution for the difference so that it was centered on 0 and had a variability of 1. Now it's been shifted to below 0, centered on about 0.78. It just so happens that the median, 50 percentile, is the same as the mean, so it's pretty. That suggests that the distribution, the posterior distribution, is pretty symmetric. But the credible interval goes from negative 1.2 to negative 0.3, so values in that range are still fairly credible. So if I were reporting that, some people take the perspective that, report the credible interval, maybe even show like the histograms. So I can say Stan hist out, and it would show the histogram of all the variables. But again, this distribution for the difference score is the one we're most interested in. So you could show that in a figure. You could put this description in, or at least what the median is and what the 95% credible interval is, in the text. If you want to go even further and make like a single decision that's kind of analogous to frequentist world of significant, not significant, that the 95% credible interval excludes 0, kind of reflects that 0 is not a very credible value for the true population difference. In
Meaning
which
that
case,
the groups are different.
yeah.
Okay.
So if you needed to then simplify your speech by saying whether there is a difference or not, you would then, in this case, say that there is a difference.
But we don't know by what magnitude.
Well, right now, that is correct. You know it in terms of magnitude of like this Z score that we created, but we need to back transform to get what the actual values were. So if this were like the blood pressure example, like how many, actually, does anybody know what the units of blood pressure are? It's on the tip of my tongue.
Sorry.
Blood pressure units?
Millimeters of mercury.
Yes, something like that. Millimeters of mercury. So if you wanted the actual raw measurement units, you have to do a back transformation. You have to undo the whatever we did to get to this scale. So what was that? Let's bring this R code over. To get to these individual values, we first subtracted the mean and then divided by this standard deviation. So we just have to reverse that. So we multiply by this standard deviation.
Don't you already have all of those values just in Y1 and Y2?
Well, what we're trying to do is get at if there is a difference of 0.78 Z scores, what is that in regular values? So
Oh, so you're gonna need it to the difference.
yeah. So
Okay.
if I say like negative 0.78, so we had it divided by that variability before. Now we multiply by again, but it's still that same thing, the variability of both.
Okay, so hold on. So the output above told us essentially that there is a difference in means between the two groups.
Yeah.
And now we're trying to find out what the magnitude of that difference
Yeah.
is, right?
Yeah.
Okay.
So this is the magnitude in terms of like effect size.
So if you need one number.
So, and we can turn these numbers from the like z-score / effect size scale back to whatever the original scale was. So if we were originally dealing with blood pressure, it'd be millibars. If we're dealing with IQ, it would be IQ numbers. Weights would be pounds. So we want to get back to that original scale, untransformed scale. So for any parameter in this list that's in effect, this is actually all you need to do. You need to just undo the division by the standard deviation. So you multiply by the standard deviation.
So the 0.78 is the
Point-
value when you divide y1 by y2?
It's the distance between the means of y1 and y2 divided by the amount of variability in the data set overall. Remember, that's how we did the original standardization. We said, here's both groups overall. Shift the data points so that they're centered on 0, or centered on whatever this value is, the mean here, so that that's on 0. But then divide so that you rescale by whatever this thing is, and we chose the variability across both groups. So we're just undoing that
So then how do
to
we
get back
the,
to
how do
these.
we get the 0.78?
It's
Ah.
on your
Up
chart.
there.
It's right there.
Okay.
So yeah, I was, whoops.
The mean value. Okay.
Yeah, I was just grabbing, like, you can do it to any of these values. So if I wanted to find out what this 2.5 percentile actually is in raw values, I'd say 122 times the SD of both. And that gets you, so it goes from negative 17 as the lower end of the 95% credible interval up to negative 0.32 times the SD both. So negative 17 to negative 4.
Okay, so when we took the mean for diff and transformed it back, and we got negative 11.
Yep.
Is that saying that the difference between the means for the two groups is 11?
Yep. just like, in fact, if we look at the data generating statements way up above, we actually sampled them from one group that has a population mean of 97, another group with a population mean of 108. So there was a true difference of 11. And we happened to get a posterior that is peaked right at that true difference of 11. You'd never know that in real life experiments because you never know what the true population values are. But it's nice to see that in our simulated data. Now, if you wanted to actually get what this location parameter was, you not only have to multiply by the SD, but also add the mean. So let's take, what is the negative, or yeah, what is the 2.5 percentile value for the intercept parameter? Well, you take that 0.24, you'd multiply it by SD both, but then you have to add in that mean both as well to get to 100. Ditto to get to the other end, 0.22 times SD both plus mean both. So 100 to 107. So what this is saying is that after we've converted back to the real values, the mean of the two groups is somewhere between 100 and 107. And the difference between the two groups is somewhere between negative 17 and negative 4.5.
So the 100 and the 107 includes the data from both groups?
This is the point, the center point between both groups is somewhere between these two values on the raw scale. And the distance between both groups, somewhere between these two values on the raw scale. So when you do that Z-score, it makes it nice, easy to specify priors and talk about the, and when you do it, yeah, it makes it easy to talk about priors, but you have to remember if you want to refer to values back on that original, the original scale of the measurement, you have to convert back just using these things. So for anything that's like a difference, all you have to do is multiply by the scaling, the denominator in your Z-score. But if you're talking about a location, you have to do that plus add in the shift that you had in the original data, the original transform.
But so if you didn't, if you just did it, without adding the mean, you could just take the number and then, your output, the negative 17, and add the mean to it, the mean for both.
Yeah, yeah.
Okay. Cool.
Yeah.
Can we at some point go over how we would actually write out the results for some
Oh,
of
sure,
these?
yeah. Here.
Because I have no idea at this point how I would
For the
write it
assignment
up.
we're doing, are you expecting a written, something to submit written, or is it just the oral presentation?
Well, no, it's definitely going to be, because the written thing is you're going to be writing up code and producing figures. And I'll need you to at the outset describe the data, where it came from, what are the questions that your code is going to address, and then, yeah, I think you'd want to have a paragraph or two on what you'd conclude, what.
But not necessarily a full introduction. Full
No.
introduction.
No.
Mike is very fancy.
Yeah.
Is it possible, I mean, I guess it's more work for you, so you have time to kind of give us a data thing to practice, because you know how you've given us assignments for other things?
Yeah,
Can you
no,
give us something
this
to-
coming Monday is going to be
Oh,
another
okay. I was gonna say.
another play.
Cool.
In fact, I'm going to send it out before
Yeah, I was gonna
Monday,
say.
so you guys can play with it.
Yeah.
I'm sure you'll
Yay.
play is an accurate description.
And if we wanted to like go back and review all these, I'm just like fuzzy now because like we've changed all the syntax and gone back, and I'm like I don't know what 1 was doing, I don't know what 2 was doing. And I just want like a plain language summary of like what each one is and like the key take home points for each one. Like, can I find that in R for data science?
No, because these are ones that I've created. Why don't we create a Google Doc where we crowdsource it amongst ourselves, a description of each one.
Awesome.
I don't know. I feel like I'll do my first attempt at summarizing things, and if you guys want to add on your perspectives, which might help
I
your
find it
colleagues.
helpful when you say this is equivalent to what he does.
Yes.
Yeah.
Okay.
Mm-hmm.
Yeah, I'm just like this is the same, you know,
This is
set of data, but we're just doing it a different way because it allows us to do this.
Yeah.
Or,
Okay.
Like super layman's terms.
Sure. Yeah. No. And that Friday time slot where it's like technically they booked off for a lab. I'm just like available anytime for you guys to drop by. I'm usually just hanging out in the Klein lab, so you can either give me a heads up ahead of time that you're going to come by, but also if that day you find you have a statistical itch to scratch, just come on by.
How many, so in terms of the data to use for a final project, how many participants do you want in that data set?
Oh, it doesn't matter.
Okay.
No.
Because I would like to run it on data we're just collecting now, but we have like 10 people.
Yeah, that's fine. No,
We have a lot of data on 10 people, but
yeah, no, that's
okay.
great.
Timeline wise, when are we gonna start needing our data set and doing stuff with it?
Well, I thought I think in terms of the syllabus, what do I have in there?
Because I think you just have the deadlines.
The last-
For,
Well, I think I have the last week as
yeah, you have
okay.
some
All
time
these
to work on
classes
it.
we are working on it to get that's time for you to have me pinned down
Okay.
here to work on it. I haven't talked about some of the more complicated models yet, so we're gonna move to repeated measures and then quickly from there growth models and things like that.
Okay.
So you haven't had a chance to be exposed to much yet. Getting the initial finding the data, doing what formatting of the data you might need.
I'm just not I have my data. I'm just not sure how to format it yet since I don't know what
Yeah, I guess.
I'll be doing.
Yes, good point. Yeah.
Because we haven't covered those testing, so I don't know.
Yeah, what structure it should be in.
Yeah.
So the next example that we'll start off with next class talks about one format that makes things really easy.
Okay.
So there are formats that make things easier than others.
Okay.
So
So
we will be talking about that as we.
Okay, so for each one as we
Yeah.
go along, you'll tell us what's
Yeah.
the best way to format for that. Okay,
Yeah.
perfect.